speaker for this session is Sebastian Reich from Potsdam, Reddit, and he's going to speak on data assimilation and Schrödinger's perspective. So thank you very much for coming, Sebastian.
Thank you. So I changed the title, as you might have noticed. So the original one was a bit bulky, so this is a bit shorter. So I call it data assimilation. So it's a talk about data estimation, methods for data estimation. So my take on this is in the debate whether it should be called filtering or data assimilation. If you come from the Ensemble-Kalman filter world, then you call it data assimilation. If you come from particle filtering, I guess you call it filtering. I mean, the two communities are merging now. I mean, thanks to meetings like this, actually, which I enjoy very much, and thanks for the invitation. So, so eventually, I guess we will coin one word, and if you then Krishan, it will be particle filtering. Anyway, so there are a few common things to both of these originally maybe sort of somewhat separated communities, and these are from a mathematical perspective that you think about particle approximations, so as interacting particle systems, and you think of mean field equations, the limit as the number of particles goes to infinity. And my sort of personal favorite twist on this story is the idea of coupling. And that's also what gives rise to the title of my talk in relation to Schrödinger. Because Schrödinger wrote a paper in 1931 where he sort of proposed a particular boundary value problem in stochastic analysis. And there's a handwritten note on this particular copy, reprint by Schrödinger himself. And it says, this is still a challenge to mathematicians to solve a certain boundary value problem, which he posed in that paper, and which I will explain in a little while. Now, of course, since then we have made, others have made a lot of progress on this problem. But it's actually very nicely related to data assimilation or sequential filtering. And that's what I want to demonstrate today, and numerical implications. But before we get to this, I like to explain to you a little bit the world of data assimilation if you come from the weather and Ensemble-Kalman filter world, so to guide you maybe a little bit in your thinking and what motivates the data assimilation community. So here's the ECMWF, the European Center, and they run, since 25 years ago, they run an ensemble prediction system where they essentially, all they do, they run a model, which is a discretized PDE, Navier-Stokes plus thermodynamics, in many copies, let's say M, and some initial conditions. Interestingly enough, the meteorologists, a lot of them don't like stochastic models. I think they like to have them to be reproducible somehow. They know the models are wrong, so they know there should be some sort of contribution that account for model errors, but they like to reproduce their errors exactly each time they do them in a way. We will come back to this in a little while, to this point. But anyway, so this has been available since sort of about 25 years ago. But the ensemble size is very, very small, so it's on the order like 50, maybe to 100. And the dimension of state space is in the billions. I think we heard this earlier in the week in Dan's talk, and also Nick mentioned it. But these things are really being used to sort of say something, what is the probability of rain today? Maybe not in Singapore. I think it's a bit hard to predict, maybe in general, but in other areas, etc. There's a very nice, if you like to read more about this, there's a very nice paper where I actually took these photographs from, or it's called The Quiet Revolution of Numerical Weather Prediction. Is a Nature paper, which goes into all the details, because it's just an amazing success story in a way, and all the things that have gone into it is quite a story. But you can't get Nobel Prizes for it, because just too many people. It's also maybe not this one major breakthrough thing, but definitely going to an ensemble prediction system was a major breakthrough. And once this system was available, people started thinking about what we could do with it. And that's when the Ensemble-Kalman filter was invented, basically just around this time. So this technology became available, and then practitioners immediately start thinking about what can we do with it. And then the ensemble Kalman filter was invented by Evanson and simultaneously by Canadians, Peter Outcomer, etc. In a nutshell, what this ensemble Kalman filter is doing is augmenting this ensemble prediction system. And in a mathematical way, it's like this. So here, F is your model. Z is a collection of all the states, temperature, density, whatever, velocity. And then there are two contributions that they typically add to such a system to make it work. So the one is the blue, which is sort of, the Z bar is the ensemble mean. This is the empirical mean of the ensemble. And then you take the difference of the mean with the actual state estimate versus its mean. And then you multiply it by the positive definite matrix Q somehow. We will find out what it is. But this is a destabilizing term. So that actually drives the ensemble even further apart. And then they also add a stabilizing term where the data actually comes in. So Y are the observations. H is the forward operator. We've seen this many times now. This is, so this is your, if you measure temperature, that's how the temperature is related to your state variables at a certain point, right? And again, there's a matrix K, which is sort of a nudging matrix, a gain matrix, etc. And I just want to go a little bit into detail on how to find these things and how it's related to what people do in weather forecasting. Historically, actually, people just took in your constant matrix, and then it's nudging. So you basically nudge your system towards what you observe. So you take the difference between what the data is and what your model would observe or predict for this particular value, Y, and then you take the difference and nudge. Okay? Okay, so now let's go a little bit more in detail in these two. First the blue, and then I will go into the red term. Okay, so this is a bit of mathematics. The end goal of this whole thing will be that I will try to argue for you that actually what meteorologists do by this blue term is a form of stochastic model error. It's just that they model it as an interacting particle system. And of course, the advantage of this is, so you mimic some sort of model error in a Brownian dynamic sense, or Brownian motion, contribution additive, but you actually make it deterministic because you model it as an interacting particle system. And so let's start then with an SDE, and with some noise term and a diffusion constant, simply a constant gamma. And I have a plus here because this is the standard, so we go forward in time, so the standard Brownian motion conditioned on the past, and the increments are sort of forward in time. And that generates a path measure, et cetera, et cetera. Now, you can also, for an ODE, you can always go backwards in time, right? With an SDE, you can do the same, but it's a little bit more complicated. And there are different variants of it, of backward SDEs, but this is a version where you, if you want to go backward in time, so you have the marginal distribution at the final time, you want to do backward in time and recover the initial distribution, then you still have an SDE, the drift has changed, and because you go backward in time, now Brownian motion is also conditioned on the future and not on the past, right? The increments are now conditioned on the, as I said, on the future, right? And you now have a final condition, which is the same as the model running forward, right? And the modified drift term has this term here, the log of the marginal distribution at time t of your forward simulation, right? Okay, and the way to see this or motivate this, why this is the case, you just look at the Fokker-Planck equation, which for the forward dynamics looks like this. So this is a drift term, this is a diffusion part. Now, if you want to rewrite this something with using Brownian motion that actually goes backward in time, that has to change the sign, so it should be a minus, but it should still be the same PDE, right? Because we want to have the same solutions, forward and backwards. And it's a PDE, so this should remain the same. So basically you have to compensate for this difference, and that's how you get the additional contribution in the B term, which involves the density itself. Now you can push this one step further. If you don't like noise at all, then you can take the average of F and B and define a drift term U, so you interpret diffusion as a drift term. But it's a mean field drift term because it involves the density U propagating the marginal of your your variable state variable z at time t, right? So there are various ways of playing around with this, and so if you go all this way, then you get this equation, which pathwise is not the same anymore as solving a SDE, right? Because the solutions are suddenly smooth, right, in time. There's no stochasticity anymore, but the marginals are still the correct ones. So if you, in weather forecasting, we're primarily interested in the marginals. We're not so much correlation in time or so. It's somewhat of interest, but primarily the marginals. And so now we work with this instead with the SDE, and you discretize this as an interacting particle system. And if you do this and you do the most simplistic approximation to your density being a Gaussian, I mean, not the density being a Gaussian, but the approximation being a Gaussian, then you get, this additional term gives rise to this, which is exactly of the form, the type that meteorologists use. And it's called inflation there. I mean, they call it inflation. All right? And so what I called Q before is now the inverse of the covariance matrix. And the mean is still here, and the gamma is sort of the strength of the inflation. It's a particular kind of inflation. I mean, meteorologists have different kinds of inflation, additive, multiplicative. So this is rather the multiplicative kind. And of course, this can easily be estimated. I mean, this is the second moment. You estimate this from your ensemble. And so you have an interacting particle system, and it mimics, in a way, a certain type of model error. Right? And meteorologists are well aware of this. Normally, their system, ensemble prediction system, would underestimate uncertainty. And that's why, from a heuristic point of view, they introduced this sort of term. But you can motivate this from saying we really start from an SD model and we take a mean field interpretation of it and then discretize with the simplest Gaussian approximation we can do. Yeah?
What's the gamma here?
The gamma is the diffusion constant. So in the SDE model, I had a diffusion constant.
Oh, so it's not natural in terms of physics?
Well, I mean, meteorologists just tune these parameters because they don't know really what the model errors are. I mean, there is an interest in estimating model errors from data assimilation, actually, by looking at the increments you get in data assimilation. So but for here, it's just a parameter. Okay, so if you want to read a little bit more about this, I mean, this forward-backward goes, I think, way back, and Nelson is certainly an early reference. Interacting things are, of course, Pierre. I talked about this in my book. Then there's a book by Cody and Andrew, etc., on data assimilation. I'm not sure why I have this here. I think it's a bit of a fetch. But there is a connection, but that would give us a different direction. So let's skip this for a moment. We can talk about this later. So this explains somehow, or it motivates the blue term that meteorologists use from a mathematical perspective. Now, how about the red term here? How do we get this? So we have data. We have likelihood. So here I assume, like, if you have like radar data, it's very high frequency. You can think of it almost as arriving continuously in time. So you can think of it as a continuous process. In fact, very high resolution models, the DWD certainly run sort of continuously a data assimilation scheme. And so we write this as an integral, with some cost function. And let's just take the Euclidean, the 2 norm of the difference. Again, there's a beta, which sort of would be related to the measurement error. For now, this is not significant. I also assume for now, actually, that the data is actually smooth in time. So this is not the standard sort of filtering setting in continuous time. We will come back to this in a second. So it's sort of an ad hoc likelihood function. Okay, so with this ad hoc likelihood function, you can do Bayes' theorem, et cetera, et cetera. And again, we just interested in the marginals. So we try to find an evolution system that regenerates these marginals that arise from this approach. Okay, and again, there's a mean field interpretation. This time, I sort of spare you a little of the details. You just have to believe me at this point, but the sort of ideas are similar to what I showed you for the Fokker-Planck equation. In any way, so you get, again, an additional term, and you basically, if you know Kushner-Sakai equation or Stratonovich equation, then you know that the filtering part is an additional contribution to the Fokker-Planck equation. And so what you want to do is to reinterpret this again as a drift term. And the drift term will involve the densities, right? So and that's exactly what you get here as well. So you get a drift term, and the conversion involves solving an elliptic PDE. So that's where basically this drift term, this additional term that you have in Kushner-Sakai, if you know the continuous time filtering equations, appears in a different form, slightly different form, because this is smooth data in time. And the elliptic problem arises because you want to interpret this as a drift term, right? So you have to solve this elliptic problem, and for this potential psi, if you have the potential psi, then this gives you the mean field equation. So bang, there you are. And then you discretize, by a Monte Carlo method. Now, of course, generally, you can try to solve this elliptic problem, but again, there's an easy way around it, where you make the Gaussian approximation. So let's assume that we approximate this conditional marginal distribution by a Gaussian. We also assume, for simplicity, that the forward operator is linear. Then you can solve this elliptic PDE analytically in closed form, and you get this thing. And we saw it earlier this week, actually, in Adrian's talk, when he talked about the ensemble-Kalman filter. So this has to be compared with what I showed you before, this nudging term. So if you look at this, there's one interesting difference compared to standard nudging. In standard nudging, you just take the difference between the observation and what your model forecasts and each individual run of the model forecasts. Here you take sort of an average between the individual forecast and its mean. That's very important for the statistics, because otherwise the spread becomes again too small. You're reducing uncertainty too quickly. The mean is, of course, not affected by this. And the Kalman gain is, or this K becomes the Kalman gain, is the covariance matrix times the forward operator transpose. This is the classic Kalman gain in Kalman-Busse filtering. And so you discretize this by a Monte Carlo method, so you get an interacting particle system. Again, all you need are first and second order moments. You estimate them empirically, and you get this system which, as I said, Adrian analyzed earlier this week in the linear setting. So if this is linear, actually he had a stochastic term here, but you can replace this. Et cetera, and there's now a lot of interest in actually analyzing such systems, what they do. They're not, they biased, right? They don't give you an exact filtering problem even as you let the particle number go to infinity, but they're still accurate and they work. So you want to have accuracy and stability results. So this is a lot of interest, and we've also done some work on it recently. Now, if you go to the standard sort of log likelihood or the standard error model for filtering continuous time, where there's actually a diffusion process involved, so Y is a rough signal. Then you can also do this for the Kushner-Stratonovich-Sakai equation, and you get the wonderful formulation called the feedback particle filter, which is due to Prashant Mehta and Sean Main and Young. And they've further developed in this. This is a beautiful thing. It's really, you take, if you're familiar with this, if you know the Kalman-Busse filter for linear filtering, it's a beautiful extension to the nonlinear case because it kept exactly the same structure. The only difference really is that the gain is changed. You have to solve an elliptic equation, and you reinterpret the classic Kalman-Busse filter in terms of a mean field equation. I mentioned this work on stability and accuracy. So this is our contribution to this rising field. And it's actually interesting, Jürgen Moser, some of you might have heard the name, a famous mathematician at ETH who worked on the KM theorem on stability of the solar system, or generally slight perturbation of integrable systems. Jürgen Moser already looked at this problem, how you can deform one density into another by sort of a dynamic interpretation. So like a mean, we would call it now a mean field flow. He had a different motivation. He wanted to just show equivalence classes of densities, so find all the densities where you can do this. But it goes certainly a long way back. And then Freddie Daum also now using this for filtering. So, okay. So this was the motivation, from this ensemble Kalman filtering world and how it links actually to mathematical objects we kind of like. Now back to discrete time. So then discrete time gets a bit more difficult and also interesting. So this has now been appeared, I think, at least 3 times or something. Interestingly enough, the arrows are going different ways sometimes. So I think most of the time the arrow goes down to the data. I think I'm the first to point the other way around. So I'm not sure if there's a preferred direction, but I see the data going into the state. But anyway, so of course you can also think the state gives rise to certain data which you compare. So anyway, so I think that's the only difference. And so the setting also we've seen a few times now. So you have, again, an additive error. This is not essential for what I'm going to talk about, but for simplicity, that's what I do because this is a standard model in data simulation. These additive errors here, you get your likelihood now in the sum, no longer an integral, and you have your Bayes theorem, etc. So now, since we do the sequential, we can basically look at a single window of this process, right? And then we just repeat it. So what are the players in this single window? So the players in this window is the meteorologists call analysis, but it's the last filtering distribution. So it's everything conditioned on the data up to that point T0, I call. So then you run your model forward to the next observation. So there's a forecast, right? Prediction or forecast. So there's the second distribution that's around. So at capital T, there's an observation. In between, there's nothing. So then you can apply Bayes theorem to this using the likelihood of the data you observe. And that's called then the new analysis, and it's going to have a hat on it. Right? So this is hat. And then, of course, you can also, just for the purpose of this window, you can also go back and think how the filtering distribution at time 0 is changed into the smoothing distribution, given that you got new data. So it's like leg 1 smoothing. Right? So these are the 4 players in the game. And we're going to see what we can do with them and how Schrödinger arises. So Schrödinger comes in as follows. So the traditional sequential Monte Carlo approach is you use your model, you do a prediction, forecast, use your Markov kernel, and then in one way or another you do Bayes with resampling, importance sampling, or whatever you want, and you get down here. So this is the traditional approach. Again, we've seen it a few times now as a backbone of pseudo-marginal, et cetera, et cetera. Now, the little bit more sophisticated way is to say, okay, well, there's something like an optimal proposal, and so in a way you can understand this in the following way, that you find a transition from the last filtering to its smoothing distribution at time 0. So you go back to the origin where you start from. I mean, for this window, right? You can do it further into the past, but I'm just going to look at one window. And then you modify your model forecast, essentially in optimal control. Right? It's an optimal control problem. To find this modification of your kernel that you used up here. So it's a modification of that kernel here, and that gets you there. And that's when you can do it, is of course preferable. Because these are closer together than those, generally speaking. But you can also try to go directly in the diagonal. You can say, well, why don't I go directly? Why can I not change my dynamics in a sort of optimal way so that the dynamics naturally, without any sort of these second steps, either at the beginning or the end, gets me from the analysis, from one analysis to the next analysis. Right? And that's Schrödinger, it's an incarnation of Schrödinger's problem that he posed in 31. Okay, so here's an example of these 3 paths. So let's say you have 11 samples, uniform in the interval -1 to 1. Then you have a number of Gaussian kernels. That's your Markov kernel for prediction. So then the superposition of these 11 Gaussian kernels, in this case, gives you something like this. You get the data, so you get this filtering distribution. If you project this back onto, you find the conditional distribution at time 0, then these samples get weighted, and it's like this. And so then you can ask yourself, okay, we know this kernel going from here to here, that's just Gaussian. Now this kernel to here is also quite easy. We'll just show you in the next slide. And then you want to have a kernel that looks, each particle, a transition kernel that gets you from this, from each of these particles directly. Then if you superimpose these kernels, give you this distribution, right? So here are the kernels for the smoothing. It's all well known. It's all Gaussian here. So what is it? It's the original Gaussian contracted a little bit because you have data. They all have the same width, contracted, and they shifted around, right? So this is a control picture. And if you do the Schrödinger thing, you get these kind of kernels, which are not even Gaussian necessarily anymore. And now they have different, they focus differently, and etc. But if you put them on top of each other, they will exactly reproduce this distribution. And you have to keep an eye on this the scaling here, so otherwise it looks a little bit like nonsense. So it's -2, so it's spread out. So you basically draw one particle of each of these kernels. And of course, the big question that probably pops immediately up in your mind is, well, how are you going to get these kernels? I mean, if they have them, then we're done, right? Then we have a modified dynamical system or stochastic process, and we just do standard sampling. There's no resampling, nothing, right? Okay, so here's another example. A double well potential, a little bit more extreme. So this is your prior. So initially you think your solution. So this is Brownian dynamics in a double well potential. The height of this barrier is sort of not too high, so particles go over it, but it's also not frequent. So particles spend time over here if they're initially there, and then eventually they hop over there, and then so initially, let's assume they pretty much in this on this well, and for some strange reason, the next observation tells you they should really be over to that side, so that the real reference solution actually jumped over to the other side. That's of course challenging, and so because this is the forecast. I mean, this is the last. I mean, this is the initial distribution. This is what the forecast the model gives you. So some particles have moved over, so your little tail over to the other side. Again, the scaling is -5 to 5 here, so it's a bit different from here. So, but most of the particles are still in this other well. Now, if you look at the analysis, it's the observation is really in the tail, so it's suddenly over there. So it's so the posterior is really this distribution, and the corresponding smoothing distribution at time 0 is shifting this towards the center somehow. So and now, of course, you see that if again there is an optimal control modification of the double well potential Brownian dynamics going from here to here, so that's in a way easy. And so resampling now goes from here to here. It's much, much easier than if you have to do resampling from here to here, right? With having just a few samples. So it's smoothing is definitely a big advantage, or the optimal proposal. But again, there's actually a controlled modification of your Brownian dynamics model that gets you directly from here to here, and that's a solution again to the Schrödinger problem. Okay, so how do we get this? Again, and that's one of the reasons why I actually introduced you at the beginning of this forward and backward SDE business, because there's this back simulation methods. Again, this was mentioned earlier this week. So in the SDE context, that basically can be understood in solving this SDE backwards, which I introduced earlier. So to get the SDE that gets you from here to here, what you need to do, you basically simulate forward your standard SDE model. In this case, it would be Brownian dynamics. So this is a potential, the gradient of the double potential with the initial distribution. And then this gives you marginals. You look at the marginals of this SDE that you generate. And then you have to solve this SDE now backwards with this correction term, which you obtain by solving the forward SDE. You solve this backward in time, and it turns out with the final condition being the posterior at the end time. And what you get at time 0 is the smoothing distribution, the P naught hat at time 0. And the control law that naturally steers you then from here to here is this one. It's the ratio of the marginals of your forward simulation and your backward simulation. I mean, numerically you might not want to do it, but mathematics is quite elegant, I find, right? So you have a forward sweep and a backward sweep. You get two marginals, you take the ratio, the log of it, and the gradient, and that gives you the control law. That's pretty standard. I mean, it's nothing new. It's standard in control theory. And so basically, that, as I said, allows us to go from here to here, but we still have to do sort of a resampling step to go from here to here. So let's see how we can directly go from here to here, and that's where Schrödinger comes in. Quite easy. This is actually not Schrödinger's original formulation. This formulation goes back to somebody in financial mathematics in Berlin, the famous guy, Vollmer. Vollmer? Yeah. So he found this equivalent formulation, I mean, of Schrödinger, which is quite nice. So basically, here's Kullback-Leibler. Again, we've seen it a few times, and Josef talked this morning. Now in path space. So P is the path space measure generated by the underlying SDE model, which is like this double-well Brownian motion dynamics thing, given also with initial distribution P naught. So this is the path measure. And you're trying now to find the best approximation in this Kullback-Leibler sense. Subject, now not that you like you do in variational base where you say I just have a subset of these densities over which I search or path measures. No, here you have boundary conditions. So you basically say I want to have a process that so derived from the original model, but it just connects two different distribution at the beginning and at the end. So you change your boundary conditions. And that's exactly what Schrödinger was asking himself. I mean, you know, you have Brownian motion and at time 0 it starts at 0, and then suddenly you observe it's somewhere. What is the probability that this arises naturally, or how do I have to change my model that this happens? And that, I mean, for Brownian, it's just Brownian motion, but you can do it for SDs as well. Okay, so we need to solve this boundary value problem and sort of a constraint minimization problem. And because it's Kullback-Leibler, we know immediately if the solution exists, it has to give rise to a control law. I mean, we're not going to change diffusion constant because then it would be not continuous with respect to the original process. So the only thing we can change is a drift term in form of an additional control law. And so now it's just a question how we get this. And it turns out it's basically just you keep iterating. I mean, we had this for the smoothing problem. I said once forward and then backward. And basically smoothing is particularly nice, or the optimal control, because the boundary conditions are sort of the right way. I mean, it allows you to go forward, and then at the other end you have the condition to go backwards. But now this is no longer the case, so you have to go forward and backward until it converges. That's one way of trying to find a solution, which is sort of a continuous incarnation of the synchron iteration, if you're familiar with this. I mean, so there's a synchron iteration, which I come back later, which is for discrete. If everything is here just a bistochastic matrix, and you want to impose sort of probability vectors on a bistochastic matrix, and it's a synchron approximation or synchron iteration you can use. So this is a continuous version of it. So, important it is that the initial distribution here is this time is unknown. This is sort of a tunable parameter you try to infer. And then you do this forward in time for an unknown, yet unknown initial distribution. And then you use the marginals you get from this to solve this backward problem. And so what you want to achieve, that you do this so that in the end, so this control law becomes so that if you go the backward sweep, you end at P naught, the original marginal distribution you want to start from, and not the smoothing, the P naught hat. Right, that's easy. But if you want to go back to P naught, then you have to keep iterating. But again, it's just the ratio of the two. Once you solve this sort of thing, the control law is the ratio of these two, one forward sweep and one backward sweep. Now it's implicit. Okay, so an example to see how this works. this is the Euler-Maruyama discretization in time. It gives rise to a transition kernel, which is Gaussian in this case, with a mean given by this here, this term. Now, we assume that we have m samples from Zn. And let's say for each of these samples, we also drawn a sample from the Euler-Maruyama scheme. So we have m pairs. So this gives, can be, if we stuck this into the transition probabilities of this Euler-Maruyama scheme, then we get a matrix Q. So we get like a finite dimensional approximation, roughly speaking, of the transitions, which is a continuous process, but now it's a matrix. Then let's say at each time step, we get an observation. So it's back to the almost continuous time observation scheme. So you get some importance weights from your likelihood function. And so you get up the Schrödinger problem then becomes basically the following. You look at a Kullback-Leibler between two stochastic matrices, or Markov transition matrix in this particular case. And Kullback-Leibler is defined like this here. And the constraints are these marginal constraints that if you sum over the first index, it should be 1 over m. So uniform weights, you want to go back to uniform weights from weighted weights or weighted particles. And so over the second index, you get the WEs, WIs, which come from the importance sampling, the likelihood function. And then you basically use this matrix P for resampling. So the matrix P you get from this is a representation of these kernels that I showed you at the beginning, which were these humps which were sort of spiking towards the middle and then going down again. So these Schrödinger transition kernels are now approximated by the column vectors of this matrix P. So each column vector is basically an approximation, discrete approximation to this kernel we're looking for. And then it's just sample from it. So you can just indeed just sample, or you do something which sort of mimics a little bit more your dynamic model, because you know that basically it should look like a discretization of your original SDE, because we know there's a control law. So basically what you want to extract from this matrix you compute here is the mean. You want to extract the drift, because the variance you already know. The variance should be what you have in the Euler-Maruyama scheme. So, and the drift you extract by computing the expectation value in each of these columns, right? And that's exactly what's written here. So this is this expectation value, right? So this is an approximation to the drift correction. Okay, so if you do this for the Lorentz 63 model, I think that hasn't featured yet here. So Lorentz 63 is this three-dimensional stochastic, deterministic originally, chaotic system that was invented or discovered by these meteorologist Lorentz in the 60s, early 60s. So it's and I added a bit of noise because for the Schrödinger picture, you need a little bit of noise. I mean, you need a diffusion process. So what do you have here? So here up here, this is the root mean square error, the estimation error. This is sample size. So this is like five ensemble members down to 20, right? So really small ensemble sizes. I mean, and this is a three-dimensional dynamical system. So so this is ensemble Kalman filter here up. So it's you see it levels off essentially already. And if you would increase particle numbers, it would not get any better. That's the bias. But it's normally pretty robust. But it's interesting enough for 5, at least in this experiments. I did it a couple of times. It failed for some reason. So there's, but I'm sure you can tweak it with inflation and all these sort of things. But anyway, so the vanilla implementation. So you get this. Then here's a standard particle filter resampling approach, and here are these two Schrödinger-based approaches. So, of course, you don't get faster convert. I mean, it's still a Monte Carlo method. But the two things are robustness you might gain. Of course, there's no rigorous analysis of this yet. And also in the constant, that the pre-constant is better. And most importantly, which I won't talk about here, which is very important to the success of the ensemble Kalman filter, is this concept of localization. So, so basically, you want to construct local updates also in your particle filter. I mean, so there's already quite a bit of work now that people show that you can do it. So you can make particle filters work in very high dimensions if you manage to localize it. And the thing that prevents you from localization is resampling, because if you like compute weights in one region and you get different set of weights in another region because you don't take the observations from this region into account here because you say, well, this is really uncorrelated. I mean, when I measure the temperature over New York, it shouldn't change the current temperature in Berlin, let's say, or Singapore for that matter. Then you would get different importance weights and you do resampling, and suddenly you have certain particles from here you have to glue together with particles from there, and it is continuous, and it's a whole mess if it's a PDE. So you want to make this continuous, and that's where this idea comes in very handily, because you can adjust these continuously, so the mean changes continuously, right? If you change the weights continuously, right? So this is a nice minimization problem here. And that noise, of course, is just a model error noise you would apply in your PDE model anyway, whatever it is, right? So you can localize this stuff. And that's, as I said, that's the key. I mean, and that's what would make this also applicable to higher dimension problems, and we're working on it. Okay, so here, the Schrödinger paper, the original one, 1932. No, I think in 1931 I said, right? So it should be a 1 here. Then there's a nice paper here that sort of summarizes what's available. There's another nice, oh, I don't list it here. There's another by Christian Leonard. Christian, yeah. He also has done very nice work on this, mathematical work. And then, of course, there are lots of related ideas floating around. There's a lot of renewed interest in twisting, and it's also changing the proposals. But I think it's still hooked to the picture of smoothing, essentially. Peter Jan, from a more practical point of view. There's a nice, if you want to read more about Schrödinger's problem, and it's linked to optimal transport, Mark Couturi is writing on a book, and it's on archive, so you can always see it. And I'm writing on an Acta in America paper. So a preliminary version I put on the archive, so you can see it there. I'm actually still revising, so it should come out next year. Okay, so where are we now? So I got how much time? 8 minutes including questions. So let's just you can also apply these ideas of using coupling ideas concepts to the standard filtering approach, and then it's basically what we heard again this morning by Josef in a different way. You try to find a map that sort of pushes your particles from one distribution to another, and he did it in the Rosenberg-Knote rearrangement, and then parameterize it. But you can do it non-parametrically using optimal transport ideas, because we know that such maps are gradients, and you can approximate them in a discrete sense. And so again, in a nutshell, you can compute a matrix, as I did for the Schrödinger problem. And this time, the cost function is a bit different. It's no Kullback-Leibler. It's a correlation that appears as a cost function. The side constraints remain the same. And so you have a minimization problem as before with the same side constraints, except the minimization function is different. And you can think of it as a limit of a Schrödinger problem as the diffusion goes to 0. And then you can use this matrix also instead of resampling. And again, the idea is that this allows for localization. So here, just the results for a higher dimensional. Oh no, this is still Lorentz 63. So this is Lorentz. Do I have? No, I didn't bring any Lorentz 96 results. So this is again Lorentz 63. Okay. Anyway, so this is sort of the same model I had before. So here's a particle filter with 15 particles now up to 35. This is now real. I mean, it's only observing the first component and only in large time intervals. So it's a much tougher filtering problem than the one I had before. So you need larger particles. And this is the ground truth if you run it with enormous number of particles. This is what the ENKF is doing. So it's very robust, but it's biased clearly. And I think the big discussion now in the various meteorological centers, including the DWD, the UK Met Office, ECMWF, whether to use particle filters or not in whatever incarnation is basically around this point. I mean, is there a regime where a particle filter can get better than the ENKF, can beat an ENKF? And there's some indication, especially by the German Met Office and also by the Swiss Met Office, especially if you talk about convection, which is a highly nonlinear three-dimensional phenomena. If you have convecting and dissolving schemes that then allow you to predict thunderstorms and stuff, which is really highly nonlinear processes and probably also very non-Gaussian distributions, that indeed you can do better than the ENKF, the sort of current gold standard. All right, again, some references here about various implementations, summary, and I guess, yes, we have assimilated enough, at least from my end for today, and thank you for your attention.
Sebastian, for your talk. Do you have any questions for the speaker?
So you mentioned that you are solving an implicit equation in each step of the method.
You mean this Schrödinger? Yeah.
So when you implement it in practice, you have to.
Yeah. So I run, and I mean, in this previous example, I mean, okay. So if I do the Schrödinger, this was the first example I showed you. That's the Synchron algorithm. I think it was actually mentioned in one of the previous talks somewhere. So it has a complexity of m squared, I believe, m the number of particles. So this is really for small ensemble sizes, let's say 100, the Met Office is running, say. I mean, if you can afford thousands of particles, I mean, you don't need to worry about this, right? Just use your standard particle filter, right? So the overhead is, I think, small compared to running a model, which is a PDE model with millions of degrees of freedom. Yeah, so this is in there where it makes sense. I mean, otherwise, yes.
When you think of this iterative algorithm for doing Schrödinger, can you think of it as a tempered version of the ensemble transform? I mean, so if you begin, for instance, with the sample sort of forecast, and then the weights are essentially degenerate, would you eventually kind of move? So if the likelihood is essentially concentrated on one part of it initially, would you overcome that by moving the
Yes. I mean, I think that would require a little bit like in Nick's talk that you rerun your model. So yes, you can basically get a first iteration gives you an idea about how to control it, but then you have to rerun to actually move stuff there, and then you can do the next loop. So there is an additional payment, and of course the question is that better than running originally like 4 times the ensemble size? And I think it's better to approximate the steering law or control law and then run the model maybe 4 times, but have the benefit of getting close to, with less particles, but being there where it should be, instead of having lots of particles where they should not be. Yeah, sure, yeah.
Any more questions? Adrian?
Can you go to slide 9?
I have to tick each time here. It's not, has no fast forward, at least not that I know of. Yeah.
So you mentioned that you use a lot less particles than you mentioned. So in practice, how do I use this
I use the pseudo inverse.
the inverse of P? So if I take the same covariance and I have a lot less particles than how do I use this?
Well, I mean, in this picture, you would do the, as I said, the pseudo inverse, and it's okay because you know, the second this here is in the image of it. Yeah, it's singular. Yes, I mean, so you're only perturbing stuff in a certain direction, but this is known for the ensemble Kalman filter. It's basically it stays in a linear subspace formed by the ensemble, right? So that's one of the reasons. Yeah, but in the SVD sense, you can invert it, right? So the pseudo-inverse exists, right? So you compute the singular value decomposition, and then in that subspace where it's non-zero, you invert, and the rest is zero. So you project it down into that subspace, but it's fine because you apply it to this object, so there's nothing bad happening here. But yes, I mean, you're only perturbing stuff in the space spanned by the particles, which is another reason why people use localization to break this, So that the updates are actually, so then basically, if you apply localization here, you would say, let's just take the diagonal elements, and hopefully all diagonal elements are non-zero. And then it has full rank. Right? So this is localization. But that makes the analysis very hard, right? I mean, you've done some work already, but it's other, I mean, Xin Tong is working on it, and but that's the holy grail to understand this.
Okay, so let's